Welcome back to this module, module 8. In the last module, we proved several properties of countable sets. In this video or in this module, we continue with more such results that will be of interest and importance in the development of the idea of real numbers. We also work out some exercises in the end of this lecture. In what follows next, we prove a theorem that says that countable union of a family of countable sets is again countable. Formally, we have theorem: if AM is a countable set for each m in the set of natural numbers, then their union, in fact the countable union m from 1 to infinity is also countable. The proof of this theorem goes exactly in the same manner as that of showing that n cross n is a countable set. Here the first thing is, there are two cases. Case 1, let all the AMs are disjoint, mutually disjoint. Then what happens? I can arrange the elements of A union M. Then what happens? I can arrange the union of AMs where AM is the set, say for example AM1, AM2, AM3 and so on and so forth. This is my AM for each m in the set of natural numbers. Because each AM is a countable set, I can list the elements of AM in this way. Therefore, what I can do, I can arrange the elements of A1 as A11, A12, A13 and so on and so forth. Similarly, I can arrange the elements of A2 as A21, A22, A23 and so on and so forth. I can arrange the elements of A3 as A31, A32, A33 and so on and so forth, and this way I can arrange all the elements. Now, it looks like the elements of n cross n. Therefore, what we can do, I take this is the first element, A11 is the first element, then A12 is the second element, A21 is the third element, A13 is the fourth, A22 is the fifth, A31 is the sixth and so on and so forth. This way what we can do, we can again make a list of all these elements together one after another, and that will be the listing of all elements in the union. And now this can be done exactly in the same manner as we have proved that n cross n is denumerable. In the same manner, we can also prove that the union of AM is denumerable, or you can say it is countable, right. Now, based on this result that countable union of countable sets is again countable, we have the most important result now, that is, the theorem says that the set Q of all rationals is countable. The set Q of all rational numbers is countable. Now, the proof goes as follows. Since n cross n is countable, we can always find a bijection Z, from n to n cross n. Now, because of the arrangement of the elements of n cross n, we can always find an injection, say F, from n cross n to the set of positive rational numbers, that is the set of positive rational numbers, and this mapping can be F of simply m by mn would be m by n. Then F of z is an injection from n to q plus. It is an injection. F of z is an injection from n into q plus, and thus q plus is denumerable. Similarly, following the same argument, we can obtain an injection from n to q minus, so that q minus is also denumerable. And what is q? Now, q is nothing but q plus union of 0, the singleton, and then q minus. As we know, this is countable or denumerable. This is countable being the finite set, and this is countable. Q minus is also countable. Therefore, this is a union of three countable sets, and by this result their union is also countable, and this completes the proof that Q is countable. Q is countable. Now, as a byproduct of what we have already proved, that n cross n is countable, n cross n is countable. We have already proved that, and based on which we have proved that Q is also countable. Now, we are using this property to show that the Cartesian product of any two countable sets is again countable. The Cartesian product of any two countable sets is again countable. How this can be proved? Suppose let A and B are two countable sets, right. Let A is also non-empty, B is also non-empty, because if they are empty, we have nothing to prove. Then there are bijections, say f from A to n and g from B to n. These are the two bijection because A and B are given to be countable. Now, consider the mapping. Let us call it H, A cross B to n cross n. How this is defined? H of A B equal to f of A, f of B. Then it is easy to show that H is a bijection. H is a bijection. And so, n cross n is being a countable set. It is a countable set. Therefore, there exists a bijection from n to n cross n, again a bijection. It is a bijection. Then consider the composite mapping. Consider the composite mapping. Consider the composite mapping phi of H from A cross B to n by phi of H of A B. A is a member of A and B is a member of capital B, which is given by phi of H of A B, and this is again a bijection, being the composition of two bijective mappings, and therefore, A cross B is also countable. it is also countable. Note that having a bijection from A to B is equivalent to having a bijection from B to A, as one can be the inverse of the other. You have already seen that we have used the bijections from A to N, and sometimes we have used bijections from N to A to show that A is countable, and they are in fact equivalent. There should not be any confusion regarding this equivalence. So, here in the case 1, already we have proved that when in the union AM, M in the set of natural numbers, in case 1 we have shown that when AM are disjoint, that is, there is no common elements. In fact, I should write this as when AMs are mutually disjoint, then this is countable. This is what we have proved in case 1. Now, in case 2, we are not imposing any extra condition other that just AMs are all countable sets. They may be disjoint or they may not be disjoint also. They may have some common elements. This is possible. Then what happens? Union of AM cannot be directly expressed as A11, A12, so that for example, something, then A21, A22, then A31, the way we did in the first case. We cannot do this because some of these elements may be common, some of them may be repeated, because we do not have mutually disjoint sets. Therefore, what we want? We take a different set, collection of sets, like let B1 be A1, B2 be A2 minus A1, B3 be A3 minus A3 minus B2, and so on. Then what we obtain? Union of Bm, M from the set of natural numbers is same as union of Am, M from the set of natural numbers. But now you can see each Bm is a countable set. Why? Because A1 is countable, therefore B1 is countable, A2 is countable, A1 is countable, so B2 is definitely countable, being the set minus of one set to the other. Then A3 minus B2, both of them are countable, so their difference is also countable, and so on and so forth. So, each Bm is a countable set, and if this is a countable set and they are all mutually disjoint, by case 1 they are disjoint. So, by case 1 union of Bm, M from the set of natural number is also countable, and therefore, immediately we can say that the union of Am, M from the set of natural numbers is also countable. Now, an interesting theorem in this framework is the Cantor's theorem, that says that for any set A, we cannot find a surjection from A onto its power set. which has some further implications as you can see in the following. So, the first, let us discuss the Cantor's theorem. If A is any set, then there is no surjection, of A onto the power set P of A of all subsets of A. So, we cannot have a surjection of A onto the power set P A of the subsets of A. This is what Cantor's theorem states. Now, for the proof, suppose there is a surjection on the contrary. Suppose there exists a surjection from A to P A on the contrary. Then for A in A, its image phi of A is a subset of A, that is phi of A is in P A. Then we have two options, either A belongs to phi of A because it's a set, or A does not belong to phi of A. Construct a set, What is that set? D. What is D? D is the set of all elements from A such that A does not belong to phi of A. That is, we are taking the second condition and we construct a set D such that this is what is happening. Now, since D is a subset of A and phi is a surjection therefore, D for under phi D must have a pre-image. There exists some A naught in A such that phi of A naught is equal to D, right. We have now two options. I will call it case 1 and case 2. Let A naught belong to D, you will see very interesting results. Suppose A naught belong to D, then by the construction of D, if A naught belong to D, then A does not belong to phi A. That means, if A is an element of D, then A does not belong to phi A. Because A naught belong to D, that means A naught does not belong to phi A. Then A naught does not belong to phi A naught, which is already given to be D. We have shown that A naught belong to D implies A naught does not belong to D, which is a contradiction. Similarly, the second case is A naught does not belong to D, then by the definition again, A naught does not belong to D means this A naught does not satisfy this condition. That means A naught does not belong to phi of A naught is not satisfied. That means A naught belongs to phi of A naught. A naught belongs to phi of A naught. But again this is D, and this means you have A naught does not belong to D, you have assumed that finally you have obtained that A naught belongs to D, which is again a contradiction, which is again a contradiction. And why this contradiction have arisen? Because we have taken that phi A is a surjection from A to P A, surjection. This is not possible. This is not possible. Therefore, there does not exist any surjection from A onto the power set of A. This is what we have proved. The Cantor's theorem has far-reaching implications. It is instrumental in showing that the power set of n is uncountable, because if n is the set of natural numbers, it is countable, but the power set of n, that means the set of all subsets of n, this is not countable. Why? Because we cannot find out a surjection from n onto P, and therefore, we cannot find out. Therefore, by that result, we can say that it is not countable. Now, we work out some exercises on what we have already learnt. The first question would be, prove that a set T1 is denumerable if and only if and only if there is a bijection from T1 to a denumerable set T2. How this can be proved? Let T1 be denumerable, there exists a bijection, say f from n to T1. Now, we need another denumerable set T2. Here, if I take in particular T2 to be the set of natural number n, then your f is the required bijection between T1 and T2, is the bijection, right, and therefore, we are done. Conversely, let Z be a bijection between T1 and T2. What I want to show? I want to show that T1 is where T2 is denumerable. I want to show that T1 is also denumerable. But because T2 is denumerable, we can always find out another bijection from N to T2, which is again a bijection because of T2 being denumerable. So, the mapping Z inverse of H from N to T1 is again a bijection, being the composite mapping of two bijections, and therefore, T1 is countable, or you can say denumerable. It is denumerable, right. Now, we have the next question. Give an example of a countable collection of finite sets whose union is not finite, right. So, in particular, if I take A n to be the set 1, 2, 3, 4 up to n, each of these A n's are finite, but if you look at the union of these A n's, this is nothing but the set of natural numbers, which is not finite, n is infinite, already we have proved it. Therefore, this is a very interesting example, and you can find out many examples are available. Right. So, here is another question. We want to show that every infinite set contains a denumerable set. Right. How to prove this? Let A be an infinite set. A be an infinite set if A is itself denumerable, there is nothing to prove. There is nothing to prove. Let A be uncountable, and therefore, there exists some x 1 in A, Define a function phi from n to A by phi of 1 equal to this x 1. Now, take the set A 1 to be A minus x 1, which is again being uncountably infinite, it should not be empty, and then there must exist some x 2 in A 1 such that I can take phi of 2 to be equal to x 2. And similarly, for each such A 2, A 3, A 4 and so forth, which are being generated from the set original set A, we can find out a sequence, or you can say a listing of elements like this x 1, x 2, x 3, x 4, a set which is of course a subset of A, and this set is denumerable. This set is denumerable, and in fact, here we are using a very important axiom, that is called axiom of choice. Axiom of choice. So, we are using this axiom of choice, and we can find out a denumerable set out of A. So, here we end this module, module 8. Till now we have discussed finite and infinite sets, then countable and uncountable sets, their properties, examples and some worked out exercises, right. In the next module, that is in module 9, we will be discussing the algebraic properties of the set of real numbers. And then in the follow up modules, we will be talking about the order properties of the real numbers, and then the completeness properties of the real numbers. With all these 3 different types of properties of the real numbers are, you have a complete picture, or you have a complete characterization of the set of real numbers.